This video presents our paper titled Parse-Augment-Distill, Learning Generalizable Bimanual Visuomotor Policies from Single Human Video. Modern approaches for visuomotor policy learning typically rely on data collection through manual teleoperation from human experts. This process is laborious, costly, and time-consuming. Further, obtained policies are usually end-to-end, therefore struggling to generalize out of distribution. Alternative approaches for scaling data involve learning from egocentric video of humans interacting with objects in the wild. Even though abundant in the web, the embodiment gap between human and robot morphologies cast this approach challenging for actual deployment. Other approaches rely on demo augmentations, where a small number of source demos is augmented to include dense spatial arrangements, typically via structured task and motion planning procedures. While effective, training policies typically requires expensive simulation rollouts with a digital twin, thus introducing a sim-to-real gap. Further, most policies using image observations still struggle to generalize across different objects and backgrounds. In our work, we propose to use key points as the underlying state representation for policy learning, which offers three important advantages. First, modern pre-trained vision models have shown impressive capabilities to identify open-world semantic correspondences, therefore offering a proxy for category-level object generalization. Second, key points abstract the scene into a low-dimensional 3D representation, which have shown to improve sample efficiency and robustness to background. Finally, key point states can be augmented through 3D rigid geometry assumption, therefore providing a simulation-free, cost-efficient method for demo augmentations. We introduce PAD, which stands for Parse-Augment-Distill. PAD is a unified framework for learning bimanual visuomotor policies from a single human video. Given a user video, PAD retargets human motion to be robot executable, generates a large-scale dataset of augmentations, and trains a lightweight policy that can autonomously complete the demonstrated task. We explicitly seek that our policy generalizes to unseen spatial arrangements, object instances, and background scene noise. PAD works in three subsequent steps. In the first step, we utilize several computer vision assets, such as hand pose estimators and key point trackers, in order to parse out key points for the motion of the hands and the related objects. The hand motions are retargeted for parallel jaw grippers, using heuristics and inverse kinematics to ensure robot executability. We calibrate the recording and robot cameras, such as the resulting state action trajectory is expressed with respect to a global reference frame which is aligned with the robot. In the second step, we vary the initial configuration of the object key points and appropriately transfer the actions from the source demo, shown in green, using bimanual task and motion planning. Special care is given to issues related to bimanual manipulation, such as novel hand-object assignments and resynchronization between the arms. In particular, our augmentation framework works through the following steps. First, the demo video is abstracted into a symbolic template, which decomposes the task into a sequence of bimanual object-centric stages. Each stage can include two asynchronous actions for each arm, shown in blue, or a single bimanually synchronized action, shown in green. The task templates declare information about which contacts with or between objects take place, in what order, and whether the two arms need to be synchronized. This approach can express general manipulation tasks, as it is independent of object semantics or skill labels. Second, each stage in the template is grounded into precise segments from the demo trajectory, where each stage includes a motion segment, shown in orange, and a skill segment, shown in blue for asynchronous and green for synchronous. Finally, the segments are augmented for arbitrary object configurations using motion planning and SE3 transforms for motion and SIL segments, respectively. Please see our paper for mode details. In the third step, we distill the generated dataset with a lightweight key point condition diffusion policy. For inference, we utilize a pre-trained key point tracker to localize the key points in real time and feed it as input to the policy. For learning the policy, we introduce KPRDT, an adapted version of recent diffusion transformers which receives 3D keypoint tracks as conditions. We evaluate our keypoint policies in 4 simulated tasks from DexMimicGen and show superior performance in terms of task success rates, sample efficiency, as well as data generation time. Please see our paper for more details. We further deploy our framework in 6 diverse, real-world bimanual tasks, such as pouring drinks, opening containers, mixing bowls, emptying vases, handing over a paper roll to be placed in a pencil case, and picking up trash to throw them in a bin. For each task, we explicitly evaluate in 3 generalization splits: novel spatial arrangements, novel object instances, and randomized scene backgrounds that might involve clutter. In the videos that follow, we show autonomous roll-ups of our one-shot policies for the different tasks and splits. We observed most common failure modes in cases of high-precision tasks, such as removing a thin container lid or placing a thick paper roll in a small case. This failure is due to the inability of the policy to handle object instances that vary significantly in shape from the demo object. Second, our augmentations and resulting policies currently don't support obstacle avoidance, which can be integrated in the future by employing suitable third-party motion planners. Third, our augmentation framework relies on the 3D rigidity assumption to generate keypoint states, and thus cannot be used for deformable objects. Finally, in its current form, our work only supports single-task policies trained from each video, and therefore there is no knowledge transfer between tasks. In the future, we would like to explore combining keypoint with language conditioning to learn multitask policies that generalize from a small collection of videos. Thank you for watching.